So the focus of this video is rotation, which is going to be kind of the next couple of chapters are going to be connected to rotation, which is in contrast to translation, which was kind of the focus of earlier chapters. So translation is where things move in a straight line, or we kind of describe them as moving in straight lines, and maybe they don't necessarily move in a straight line, but we describe their motion for the perspective of moving in like a two-dimensional coordinate plane. And in that coordinate plane, they have translational motion where they're traveling and they're not fixed to some axis, so they're not traveling about some axis. Okay, the focus of rotation is motion that is about an axis, and it could be, the axis could be changing, or the radius of that rotation could be changing, but we're looking at it from the perspective of being fixed to an axis. And on that same note, we can take translational motion and we can analyze it from the perspective of rotation, but it doesn't always make sense to. But we will see some examples where we take problems involving translation and treat them as if they were rotation. So the focus of this video is going to be the relationship between translational quantities and rotational quantities, and there's some really interesting things that pop up here. Okay, and so we'll start by just listing all of these translational variables that we're familiar with. When we work with kinematics, these are the quantities we use: position, displacement, velocity. Sometimes we'll talk about average velocity, instantaneous acceleration, average acceleration, and time. Okay, and so now the focus is going to be to look at the rotational counterparts. Okay, so the first one I want to show you is position. So we can have a position on a number line, just like we can have a position on a circle. And while the position here is measured in some distance, maybe from, if this is 0, so that would be a position of 2 then. This is measured in how far away it is, how far away the angle is from 0 degrees. Okay, and so that would be called angular position. And just like we can have a change in position, displacement delta x, we can have a change in angular position, delta theta. Okay, so like if this was right here theta 2, and this was theta 1, then theta 2 minus theta 1 would be equal to the change in angular position. Okay, so that'd be like our angular displacement. Okay, so just like we have position and displacement on a number line, we have position and displacement on a circle using angles. And one thing to mention, when we talk about rotation, just like on a number line, traditionally we're going to say that right is positive and left is negative. Traditionally on a circle, the convention is that counterclockwise is positive and clockwise is negative. And that's the convention that we use. So if you're to remember this, just think clocks are negative. Okay, if you see that clock ticking, it's moving in the negative rotational direction. Okay, there's another quantity that we're going to talk about that is kind of a connection between the two of them, translation and rotation, and we use the letter S for it, and it's just distance around the circumference. Okay, and it's not distance in a straight line like displacement gives you. This is just how far around the circle. Okay, and it's going to pop up a couple times in this chapter. We're not going to use it a whole bunch. Sometimes I just use X still, even though it's technically S because it's not in a straight line. Okay, and this is the symbol for distance. Okay. In addition, we can have velocity. So we have angular velocity and average angular velocity, which is just the change in angular position over time, or d theta dt for instantaneous. Okay, we have angular acceleration and average angular acceleration, which is change in omega over time, or d omega dt. Okay, and then time, of course, is going to be a scalar. It applies to both scenarios. Okay, and so here's kind of the comparison, and we'll focus on all of these. And there's a tool that we can use to relate position, or displacement and angular displacement, velocity and angular velocity, acceleration, angular acceleration. And then we're going to focus on that next. The tool in physics that we use to connect translational to rotational quantities is radians. And this is why radians are important and why we use them all. And I will just tell you this before we continue. I did not understand the purpose of radians until I took a physics class in college and had to use them in the context of physics. And so you probably have heard of them before. You may know exactly why we use them, but the focus of the rest of this video is going to be on radians, what they are and why we use them. And so we're going to start off just with the basic definition of a radian. So the definition of radian is that the arc along a circle, a radian is defined as the angle for which the arc of a circle is equal to one radius. So this is the angle, and this is the arc. The length of this arc is r, same as this length right there. Okay, and so if you can have a stretch of circle with radius r, then that it has a length, an arc length of r, then that would be defined as a radian. And so the reason this is useful is if you think about changing the size of a circle. Okay, so if we have like a much bigger circle, okay, well this is still going to apply. 1 radian would still represent 1 arc length along this circle. Okay, and so the reason this is good is because we can then say that if we know how many radians we have around the circle, we can say that, well, this is how far around the circle, or what the distance around the circle is. So it has a relationship like this, that distance around the circle s is equal to r times theta. And so if you take any angular measurement in radians for theta, in radians per second for velocity, and radians per second squared for acceleration, and multiply by the radius, you end up with the linear quantity. Okay, and this is why we use radians. So before we dig deeper into that, I'm going to show you a couple of kind of animations of it to hopefully help it click. We have a circle, okay, and so I'm just going to kind of step through it. If we take the radius of a circle and we map it against the outside of the circle, then that arc length and that slice of pi represents 1 radius, or 1 radian. Okay, and so let me show you again. So we took the radius and we mapped it up against the arc of the circle, and so this distance, this slice of pi, has an angle of 1 radian, and if we stick them around the circle, there are 6.28 radians. Okay, so here's another illustration of it, not this one. Okay, so this is from Wikipedia, and this is like a GIF basically of a radian and drawing radians. So we take the radius and we map it against the outside of the circle, and that gives us 1 radian. Okay, and then if we were to fill in the circle, we get that half the circle is pi radians, and a full circle would be 2 pi radians. Okay, you're welcome to rewatch any of these segments here if they help you to understand it, okay? So we're going to make some connections here before we wrap up the video. But here's some of the conclusions that we can draw from this. So if there are 2 pi radians in one full circle, so one full circle is equal to 2 pi radians. All we have to do is multiply by a radius to get the distance around. So the distance around the circle then is going to be equal to 2 pi times the radius. And that's why the circumference of a circle is 2 pi times the radius. And that's why the circumference divided by the radius is equal to 2 pi. Okay, and really this is where we get pi from right here. And so radians are kind of leveraging this relationship to allow us to easily go between an angle and a distance. Okay? And so let's say we make go 3 radians around the circle. If we know the radius, we multiply the radius by 3. Okay? What also means that we can have a relationship between angular velocity and linear velocity, again by multiplying by the radius. And the same thing with acceleration. The relationship between linear acceleration and angular acceleration means multiply by the radius. And so what this means is if we have an average, or if let's say we have some instantaneous angular speed at say some time, well, what that's going to do is this is going to give you the magnitude of the angular velocity at a certain of the linear velocity at a certain instant. Okay? And then here, when we get, if we used average angular velocity, this would give us an average speed, not an average velocity. Okay, that part's a little bit tricky. Okay? But the thing that I want you to take away from here is this powerful relationship between angular and linear quantities, because this is why we use radians. This is what makes them convenient, and we're going to use them for these rotation chapters to go between angular and linear measurements through these 3 relationships. Okay? Please let me know if you have any questions.